Alright, in this video I'm going to record a video to show how to model a pressure vessel, a cylindrical pressure vessel in ANSYS workbench. So alright. This is to serve our lab, pressure vessel lab. As first part of the lab, the students are supposed to practice model a class activity, FEA model of an example cylindrical pressure vessel. So the thickness of this vessel is 1 centimeter. You see the cylindrical portion length is 2 meters, and the radius of the sphere is 1 meter. So we want to model this and apply 10 atmospheric pressure to it, which is equivalent to 1 megapascal, and see the stresses and compare them with the theory that we learned in 309 lecture part. Then for experiment, students are going to use this pressure vessel, but for this they have to make measurement and repeat what we are doing here. So I want to show you guys how to model this in workbench. All right. So all right, for this modeling I'm gonna take advantage of symmetry, and this is what we always try to do, because if you take advantage of symmetry, your model is going to be smaller. Model means less number of elements, and then less number of elements means no stresses. I'm sorry, small number, it means that your modeling and simulation is going to be done faster. So general material, if I'm going to use structural steel, I'm going to go here. So this is I made a structural steel my material, so go to geometry now. Since this model, it has the thickness of the cylinder is thin compared to overall size. We can model it using shell elements, but I want to show you how to do this actually using solid elements. So for that modeling, I'm going to model like a solid model. Students can model this in SolidWorks and import it here, but I'd like to do it here. All right, so let's go. I want to, for units, you can come here and change the unit to metric. Probably, we can leave it in millimeter. So, and mass, let's change it to kilogram. Oh no, let's leave everything as is. All right, so to model this, at first I start the cylindrical part. I'm gonna make a face and then try to revolve it about x-axis. So this is like 1,000, and then I go here 1,000 in this direction. Okay, it's like right now locked, it's lagging. So let me 1,000, 90 degree, 1,000. And then the last piece is like this. All right, so then for sphere part, I have this. All right, and then to trim away, I need an auxiliary line that goes all the way here. So now I'm going to trim away what I don't need, okay? So trim away this guy, trim away this guy, trim away. Yeah, all right, trim away this line. I'm going to need another line. All right, so I did this, but I need to make face, and the thickness is going to be 1/10 millimeter. So I need to repeat this line. I need to have a line here, continue that, extend that line. Like how much we should move? 10 millimeter. And then after that, I have to go straight in this direction again. 1,000. And then after that, okay, I need to make another circle. This time the radius is going to be 1,010. Right? So diameter is going to be 2020. Alright, I need to trim away again the part I don't need. I think we are going to need an auxiliary line here to trim away the piece I don't need. See here, I need to connect these two lines, these 2 points to each other. And then now I can use trim away. Right, so let's make this. What else I don't need? I don't need this also. I don't need this either. Alright, we are done. Okay, but I'm gonna need something here. I'm gonna need to trim away this guy and this guy. Alright, I think we are ready. So let's zoom extend. Yeah, I'm not gonna need this line, and I'm not gonna need this line. Alright, so we have this face. I'm gonna revolve it about x-axis, and that's gonna give me my model in a little bit. I'm holding the control so that we select the faces, both faces, and then I'm going to revolve it for 90 degrees. All right, so now let's zoom extend, see what we have. All right, so as I said, now this is 1/8 of my cylinder with the thickness, and we have a solid model. Okay, so let's close this and go back to mechanical thing. Okay, so the geometry done. Go to modeling environment. And all right, so we wait until the modeling environment opens. Okay, it's taking time. We wait. Okay, it's coming up. All right, this is our model. Okay, so the geometry. Oh, yeah, we have not assigned the material. So let's assign a structural steel. So, and then now let's mesh it. We can mesh it. Generate a mesh. Let's see what happens. All right, so this is my model. And then now I'm gonna apply boundary conditions. So for deformation, not deformation, the boundary condition will insert fixed support. Now we're gonna apply displacement. Taking advantage of symmetry, as I said, this face that I see here, this guy, this shouldn't move in Z direction. So I'm gonna select that and say that guy will not move in Z direction. And then another displacement I'm gonna do is, I'm gonna say displacement face. This one shouldn't move in the one in Y direction. And then this guy shouldn't move in X direction. All right, so, okay, we applied displacement, but I need to have a pressure too. The pressure to both pieces, the cylindrical piece and the spherical piece. We are gonna apply pressure of 1 megapascal. All right, so we applied the pressure, so we should be able to solve it now. All right, so let's solve it. All right, deformation is something I always take a look at first. All right, so to make sure the deformation makes sense. Yeah, okay, it makes sense. Now I wanna plot the stresses. If you do a hand calculation for this, you can find the stresses. So, you know, the stresses, what makes more sense is to have a coordinate, cylindrical coordinate system is going to help us better. So let's define a coordinate system here, cylindrical coordinate system, and plot the stresses in that one. So go Cartesian, go cylindrical. Okay. By changing global coordinates, I want to define this. So origin, let's say it stays the same, right? Origin of the cylindrical coordinate. Right now, what I have is this. Let me see. No, this is not going to do the job. We have to see x-axis as primary axis, but our primary axis must be z. So by global z. Now this is gonna do the job. So stress along z-axis is gonna give us normal stresses. I mean, like axial stresses, and about y is gonna give us tangential stress. Maybe we can, yeah, I can leave it as is, that's fine. All right, so now let's see stresses. So stresses, normal stress, I'm gonna select, okay, as I said, I wanna use my coordinate system I defined, I didn't name it, but it could say cylindrical. Okay, cylindrical. For that, I'm going to use the cylindrical coordinate system. Along y-axis is going to be my tangential stress. I know that that's going to be 2 times of stress along z-axis. All right, so let's plot this. And it's going to be uniform, right? Along the cylinder, it's going to be uniform. And when it goes to the sphere, that stress in the sphere should be half of what I have in the cylinder. So let's see. I have here 99, right? 99 megapascal. Here I should have almost half of it. There is room here to improve my mesh, but you see that consistency here. All right, and close to the edge we have different. And then I come here, I do stress along, that was Z axis. I want to do along Y axis. Y axis, that in that coordinate system, cylindrical coordinate, is going to be tangential. Tangential, you guys know that is going to be same for the cylinder and the sphere, right? So let's look at this. Let me see if I have it right. Solution coordinate system. I'm sorry, we have to change it to cylindrical. And then now let's plot it. Okay, now this is right. All right, so y coordinate now, and my cylindrical is like tangential. Okay, let me double check. This one was, oh, I'm sorry. The first one was tangential. This one I want to make it like axial. So the axial Z1. Let's see what happens. So along the Z axis, look at the Z. Z is axial. So for the cylinder, I have 50. And for the sphere, actually, this is not going to give us the axial. So for cylindrical, this is not going to work, right? Because Z-axis, which I'm looking at right now, on the cylinder is going to give me my axial stress, which I know is going to be, you see, it's like almost 50. It's going to be half of hoop stress or, right, hoop, half of tangential stress, which is right. And, right, so this is tangential stress. Stress on the sphere, I know that is going to be half of tangential stress in the cylinder, and it's going to be equal to axial stress in the cylinder. So everything looks good in here. Okay, so yeah, so as you saw how to do cylindrical system and plot the results like that. So again, I repeat, for Z-axis, no, along the axis, on the sphere, it's not going to work, right? All right, on the sphere, the stress is uniform in all directions, and it's going to be equal to 49 or 50 if I modify my mesh. I'm going to have these numbers merged to converge to 50 and 100. All right, so this is how we do that. And the good thing with solid model is now I can define a path here. I can come here and define a path here. Construction geometry, define a path, and plot the stress along the path. Then the student can see how the stress, whichever stress you're interested, is gonna change, alter along the thickness of the vessel. Right? So students can do that. And we can do that using our cylindrical coordinate system. It's gonna work better. Right? Okay, so I hope you find this useful.